This last lesson, or unit rather, is on recursion. Um, so we're going to jump into a little bit of math here first to help you understand what this recursion thing is, because you've done recursion in Algebra 2 or pre-calc at some point here. So in those classes, you did something like write a recursive definition for the sequence -1, 2, 5, 8. And then you would contrast that with writing a direct formula for that same sequence. So a recursive formula would look like this. You would say, well, to get the nth number in the sequence, you take the previous number in the sequence, or n minus 1, and add 3 to it. And so then if I asked you for like the fourth number in the sequence, you'd be like, well, if you want the fourth number, take the third number and add 3. But then you need to know what the third number is. So you say, well, to get the third number, take the second number and add 3. Then you need to know what the second number is. To get the second number, you take the first number and add 3. Then you need to know what the first number is. So a part of any recursive definition has to be some sort of starting point, or what's called a base case. So in this one, we would say the first number is -1, and then we can go from there and build that sequence. Now contrast that with a direct formula for the same sequence. That would look like this. We'd just be doing 3n minus 2. So if we plugged in a 1, sorry, 3n minus 4. If we plugged in a 1, we would multiply 3 times 1 and subtract 4, and we would get our -1 answer. Here, if I asked you for the 10th number in the sequence, you would be able to get it directly by taking 3 times 10 and subtracting 4. Whereas with the recursive definition, you would have to work your way all the way back from the 10th number down to the first number before you can get back to the 10th number and figure out what it is. So why do we want recursive formulas then when it's so much work to use them? Well, some problems and sequences are much, much easier to describe in a recursive fashion. So what does recursion actually mean? It means it's self-referencing, it calls itself. So when we write a recursive math formula, in order to figure out a value in the formula, we have to reference a previous value in the sequence. Whereas with a direct one, we just reference the index of that value. So a couple of classic recursive definitions are when you're doing numbers in the Fibonacci sequence and when you're doing factorials. So Fibonacci sequence goes 1, 1, 2, 3, 5, 8, 13, etc., etc. If you take a look at that sequence, try to figure out what's going on. Perhaps you've already seen the Fibonacci sequence before. But what's happening is we add 2 numbers to get the next number in the sequence. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. So if I want the nth number in the Fibonacci sequence, I have to take the n minus 1 number and add it to the n minus 2 number. And that's the formula. It's just saying add the previous 2 values. Now, coming up with a direct formula for the Fibonacci sequence is much, much more involved and much more confusing. This definition is very easy. It's like, hey, just add those previous 2 numbers and you got it. Now, again, with any recursive definition, we need base cases. So we need to say, in this case, we need to say f1 is 1 and f2 is also 1. The first and second numbers are both 1. If you don't know the first and second numbers, you can't generate the rest of the numbers in the sequence. With factorials, factorials is 5 factorial is 5 times 4 times 3 times 2 times 1, so on. So if I'm trying to get n factorial, you multiply n times n minus 1 factorial, like that. So then, of course, you need to know what n minus 1 factorial is, which would be n minus 2 factorial times n minus 1, and so on and so on, like that. And then with a base case, 1 factorial is 1, 2 factorial is 2, and then you can build from there. Okay. So now we're going to switch over to some coding and see what this looks like in computer science. Now that hopefully you have an idea of what this means in general. Again, recursion means self-referencing or calling oneself in the definition of a function. We're going to do that in Java. Okay. So I have written a function called printVals here, and it takes one integer as the parameter. And what I'm going to do is I'm going to print out the parameter, and then I'm going to call myself. So the function is printVals, call printVals within printVals. What do you think this is going to do? Well, of course it matters, what I send, right? If I just did like in, what would happen? Print-vals in, we'd print in, we'd call print-vals in, and I think it's pretty obvious we would end up just in an infinite cycle of printing whatever that number was. Now, what if I did this though? If I did print-vals in minus 1, if I called print-vals 4, we'd print 4, and then we'd call print-vals 3, and we'd print 3, and we'd call print-vals 2, we'd print 2, and so on and so on. Now, you should still be able to see that this will be an infinite loop because it's just going to get into the negatives and keep going and going. So, as I referenced with our math, we need a base case in every situation. In other words, a stopping point for our coding. So we could do something like this. If n equals 0, well, we can go if n is bigger than 0, we'll do this stuff. So that if it's not bigger than 0, we won't call the function again. We'll be done. So I'm going to go ahead and play that, see what we get. And as you might have suspected, we get 4, 3, 2, 1. It doesn't print 0 because it only prints if it's bigger than 0. So it's kind of like a loop, right? If you read up on recursion, you'll see people comparing recursion versus iteration or loops, like for loops. And you'll want to know when to use one or the other. Something I'll tell you right away here is the use for recursion is rare. Okay, it's not something that you just want to apply all over the place. And one of the big reasons is because it's actually really slow. Really, really slow. Unless you do it in a particular way, which we're not going to get into. So in general, recursion is actually really slow. You want to use while loops or for loops if possible. But there are some problems like the Fibonacci sequence and things like that that are difficult to do without recursion. And so it does come in handy sometimes. Really quickly before we move on, I want to show you something. If we switch around the two lines, if we call print-vals in minus 1 before printing, this might be kind of weird. Watch this. So keep in mind we're calling print-vals 4, which sends a 4. And then right away, we're going to call print vals 3. What do you think is going to happen? What's print vals 3 going to do? It's going to call print vals 3, which would then call print vals 2, and so on and so on. So remember, we were counting down here, 4, 3, 2, 1. Watch what happens when I switch the order. We get 1, 2, 3, 4. The order of the numbers switches because print vals 4 calls print vals 3, which calls print vals 2, which calls print vals 1. Print vals 1 calls print vals 0. 0 doesn't do anything. It literally does nothing. So that one's done. And then what we do is we actually work our way back up what's called the stack. There's a stack of functions that are in the middle of operating, and you work your way down to the bottom, and then you actually work your way back up to the top of the stack, starting from the bottom. So print vals 0 does nothing. We go back to where we were called from, which was print vals 1, and print vals 1 actually prints 1. And then that one's done. Where did that one get called from? It got called from print vals 2 and prints 2. And where did that one get called from? Print vals 3, which prints 3. And where did that one get called from? Print vals 4, which prints 4. So the order of your commands and stuff like this is really, really important. All right, quickly we're going to write a little factorial, Fibonacci function here. So this one is going to return an integer. So again, we're asking for like the nth Fibonacci number. So when I call it, I will do system.out.print Fibonacci, and let's say we want the 7th Fibonacci number. Okay. So this is where maybe it gets a little hard to wrap your head around. In order to calculate the nth Fibonacci number, remind you, we need to add together the previous 2 Fibonacci numbers. Okay? So we're not really going to do any calculations here. We're just going to say, go add the previous 2 numbers. And that's your answer. And we're going to return a value here. So we would say something like return Fibonacci. What do you think I'm going to put here? I'm going to go n minus 1, but also Fibonacci n minus 2. And this creates 2 branches. And this is where recursion can get really, really slow. It's because we're creating these 2 branches. It's going to make a tree of Fibonacci calls. So if I call Fibonacci 7, it's going to call Fibonacci 6 and Fibonacci 5. Fibonacci 6 is going to call 5 and 4, and then each of those is going to make 2 calls, and each of those is going to make 2 calls, and that's not even talking about this other side, which is also going to make 2 calls and 2 calls. And you can see how the calls exponentially grow. Now this isn't good enough because this is just going to generate what's called infinite recursion. We don't want that. We don't want to go down, down, down forever. We need a base case, a stopping point. So just like in math, where our stopping point is defined as the first couple numbers in the sequence, we will do the same thing. If we get to a certain point, like n equals 1 or n equals 2, we will just tell them the answer. So if n equals 1, return 1. If n equals 2, return 1. They're both returning 1 because those are the first 2 numbers in the Fibonacci sequence. If you ask me what's Fibonacci 1, I will say 1. If you ask me what's Fibonacci 2, I will say 2. So in those 2 base cases, we will not call ourselves because we'll be directly returning an answer. Okay. Let's see if this works. Hey, 13. 1, 2, 3, 4, 5,